All right, welcome back. Today, or this week, I think we'll get started a little bit on concurrent programming. We'll see how far we get. We have many weeks to go to learn this stuff, but we were dealing with this program closest last time, and I thought there was a lot more interesting details and tricks that we can learn from this program. So we'll just kind of continue along that and see how fast we can make it go. I think for those of you who left, let's see, what was it I introduced? I can't remember what the last little piece was.
Weren't you creating a cache?
Well, we created a cache. That made it a lot faster. But then there was there was this reciprocal. Like we were trying to get rid of the division. There was 1 divided by dx times dx plus dy plus dy times dy, and that was it's a big computation, and you do it over and over for every line. And what's the point? So we were introducing that into the cache. But then it turned out didn't actually make it that much faster. It increased, and most of you had left by then, but it went from maybe 1.5 seconds to 1.3 seconds, something like that, which is still better than the 2 minutes we started with, but I think we can still do better. All right, but before we get to that part, I wanted to talk a little bit about the homework. Who's gotten started? Okay, that's good. It's a kind of a tricky homework. It's not that the problems, like the programs, are not that complicated, but what's tricky about it is this whole idea of the hypotheses and the experiments and kind of getting that right. Honestly, it's the first time I do a homework like that too, so we're gonna have to see how it works out. But the overall guidance I have to give is basically try to follow the protocol. And the reason you want to follow the protocol is that it's easy to come up with the wrong hypothesis if you base the hypothesis on your test. Right? You come up with you run something, or maybe you look at the assembly, right? And then you see, oh yeah, it's going faster because it replaces all the multiplications with shifts, right? And so your hypothesis is that, right? But now you have to, that's no good. Well, maybe that's good. But you have to test it. You have to come up with a new test. You can't use the same program you just disassembled to test your hypothesis, because you've made the hypothesis based on that. So maybe now you change it so that it's no longer multiplying by factors of 2. You change it so it's multiplying by factors of 3, or multiples of 3. And then it turns out, oh, it's not doing this shifting anymore. That wasn't why, right? Or maybe that was why. Maybe the compiler does it only on powers of 2. So then the prediction is it won't work on powers of 3, right? Anyway, the point is try to make a new test once you have your hypothesis. Come up with an independent test. Yeah.
So what I was struggling with was like what the right time was. Like you're kind of talking about right now, what the time is to make the hypothesis. Like is it, say you run you time both programs, you run both of them, and then maybe you look at the assembly and see what is going on. At that point, do you make the hypothesis about?
Anytime you want. Like you can run as many things. You probably come up with some hypothesis in your head in the beginning. Like you just see the program and you know, oh, I'm optimizing. So it's gonna use faster instructions, right? And you think that's your hypothesis. And then you look at the assembly. It turns out no, it wasn't faster instructions. It was fewer instructions. Okay, so now you have to change your hypothesis. That's fine. Your hypothesis is based on this other assembly, but now you have to come up with a new experiment, right, to prove this new hypothesis. And yeah, that can be a little hairy. I think the further you go, the more steps you take, the harder it becomes to come up with a new independent test, because maybe there aren't that many ways to test this program. But if you kind of generalize your hypothesis, you can probably come up with something. So for example, someone mentioned, I think it was Bargov mentioned, in the first test, there's a printf. Like there was a little suggestion, like maybe you want to try this with printf and see what happens. And so we tried it with printf. You could use that as a test. Right? If you can have a hypothesis, and then there's this hint, well, printf, okay, let me put printf in there. My hypothesis says that with printf in there, it should go 100 times slower, right? And then you try it, and it doesn't, so hypothesis was wrong, right? But then you see, look at the code, and you see, oh, that's what happened, right? Probably isn't related to printf, so maybe you can generalize it beyond printf, right? So if I do an assignment in this way, probably it should, or if I change the variable to be allocated on the stack instead of the heap, then it would do this according to the hypothesis. Like, you can probably try to generalize your hypothesis and come up with a better test. That's all I have to offer, really, I think. Yeah?
And the other thing I was wondering about is, like, when are you, like, done? Like, at what point do you have enough evidence for what is actually happening?
Yeah, that's a really hard one. I mean, I think scientists struggle with that too. We're not really scientists. We call ourselves computer scientists, but it's really engineering. We're building human artifacts, and we're studying those. But this artifact is so hideously complicated that it's approaching the natural sciences again. So in the natural sciences, my understanding is you come up with a cool hypothesis, like, oh, gravity bends light, right? And then by this much, right? And then you look at some light, and you see it got bent, and for the first time, because you didn't have that when you came up with the hypothesis. We're talking about Einstein here, of course. So now you come up with an experiment where you can actually see gravity bending the light, and you see, oh, it did it. So that's good, but do you know that this is the exact formulation that's right? Or is it just under these circumstances? What if the gravity is much bigger, right? Maybe it doesn't work that way for a black hole anymore. It only works for like big stars, or I don't know, right? So it's the same thing there. You have to kind of live with it, convince yourself that it's probably right, try a few different things, it makes sense, right? And then kind of leave it alone until someone comes up with a counterexample, I guess, yeah.
Okay, thank you.
In the sciences, the counterexamples, that's where real progress is made. For us, I don't know. But it can certainly make life more interesting. Okay, any other questions on the homework? All right, make sure if you aren't already using Piazza, make sure to follow the discussion on Piazza. There isn't that much yet. I would encourage you to ask more questions on Piazza, discuss on there. But there was, for example, there was a typo in the homework 2 description. Someone caught it, and that's a good way to communicate this sort of thing. It was a copy-paste error, even worse than typo. All right, so let's try this thing. So we've studied a bit of this internal parallelism and concurrency, and the reason we need to know that is because the tools aren't perfect. I was talking to someone just before class about perf. So you get these. It says like, oh, you spent 50% of your time on this comparison, all right? But a comparison takes one instruction, one cycle. So what's the deal? If you don't understand, or at least have a general understanding of how the underlying concurrency works in the machine, it's really hard to get why are we spending so much time on this comparison when it should take one cycle. The reason is that this comparison is waiting for some other slow dependencies, right? But if you don't have that then maybe you will read the perf output and actually think that this comparison is the problem. Let me eliminate the comparison and I will fix everything. Probably what you need to do is speed up the dependencies if you can. Okay, so what we'll do after all this single-threaded work is kind of dive into the concurrent stuff, which is more and less complicated. It's pretty easy to get going, but the understanding performance gets hairier. And so maybe we'll see a little bit of that today. All right, so to reiterate, what we're doing here was we have this simple program that runs through a whole bunch of lines. Those are point pairs, and it compares, or it figures out the distance between each one of those lines and a point that is provided by the user, and we want to find the closest one. That's the whole program. Pretty stupid. We built a cache so that, in fact, let's, so that we don't have to parse this. All these lines, they come in as ASCII text. So we have to parse that, and it turned out that took up most of the time. So we built a little cache that has a binary image of this array of lines, just a whole bunch of doubles, but it's actually sitting there in a file now. So we mmap in the file, and then we went from like 2-3 minutes of execution time to a couple seconds or something. We pulled a couple of other tricks, and now we're down to maybe 1.3 or something like that. Let's see. So now we're going through 100 million lines. I think we started out with much less than that. But as the program sped up, we increased the amount of data. So, okay, so now we're at 1.2. Yeah. Yeah. So this is what I wanted to show you now, just to make sure. There's nothing else running. This is actually a lab machine. In fact, I'm going to ask my PhD students to not use it. Okay, I just asked them to not use it for the next 1 hour, because that can really confuse our results. And that's actually an important point. If you're running this on a cloud machine, like you're renting a VM from someone, that VM is running together with a whole bunch of other machines. You have no idea what's going on, basically. You might be sharing a CPU with someone else. You might be swapped out in the middle of your execution. You can't really measure performance at this level when you're working with virtual machines. And we have a special case here where we have virtual machines on your own laptop. That's pretty safe, unless you're like, I don't know, running a movie in the background or whatnot. Like, as long as your laptop isn't too busy, and as long as your performance counters are working properly, you should be okay. It's just on a co-located virtual machines on some cloud providers, different story. And I'm mentioning this because a lot of industry is moving that direction. So your mileage may vary. Okay, we work only with native machines for research papers. For big industry stuff, I guess you don't share with people you don't know, right? You have 10,000 machines of your own, and you run on that, and you make sure that your workloads don't collide, perhaps. All right, so okay, so my point here was, check this out. What's going on? I saw 2 seconds, 1.1, 1.4. This is pretty good, 1.1. Let me do a couple more times, see if it comes back to 1.4. Oh, there it is. Right. And this is not because anything else is running on the computer. What could be happening? I want to nail this one first so that we can get reliable performance measurements for the rest. So this is a multi-core machine. In fact, it's more than a multi-core machine. I don't know if I drew this thing with sockets. I probably did. Let's see if I have it. Nope. All right. So this machine looks like this. So we have 4 chips. Each chip has 8 cores in it. And then every core can run 2 hardware threads. That's the hyper-threading thing, where they're sharing resources in the same core. But so there's 4 sockets on the motherboard, and between them, there are these QPI links. They're called Quick Path Interconnect. Doesn't matter, but interconnect is a good word to remember. And the topology is like that. It doesn't have to be that. There's different topologies, but this is a popular one, and Intel is going with this for now. Okay, so what's happening is we have this file. It's been mmapped. Oh, yeah. And then we have the memory. I could have sworn I drew this, but maybe the file got lost somewhere. Okay, so here's, let's call this memory bus. And here's our DRAM. And then we have your QPI interconnects. In fact, the I is interconnect. So, but anyway, in fact, I should stick to my principles. Oh, QP interconnects. All right. Okay, so we have this file. It's been mapped into memory many times. So the OS decides to keep it in memory. Like the OS likes to have things in cache. So there's a disk cache, and you won't be reading this file from the disk every time. The first time we ran this, it was slow. But then every time after that, it's already in memory. It wasn't that big. It was, let's see, 100 million, and then each one would be 8 bytes, or maybe a little more, maybe 20 bytes. Yeah. So it's a couple gigabytes. So it's just sitting in memory. But which memory is the question? So these were pages of memory that were allocated when we mapped this file into memory the first time. So if the program was running over here, the CPU or the OS will pick some memory that's handy. Right? And handy in this case means nearby. So this one, there's another memory bus here. So if the process was running over here, it would allocate memory from here to hold the memory map line. And that would just stick around in memory until we need the memory again, which on this machine with 256 gigs and no users, it'll stick there for a while. Okay, so it's the file sitting here. And the next time we start up the program, it starts up on the same core, and it's really quick. Mapping this in, it's just setting some page table entries and accessing it really fast because it's on this local memory bus. But next time we run it, it starts over here. Right? And so now, mapping it in is still fast. It's just a bunch of page table entries. But when we start accessing it, it has to ask over this QP interconnect. It has to make a request saying, oh, please read this cache line for me from your memory. And then it comes back, yeah, okay, here's the cache line. Right? For every one of these accesses. So if we use if we start running on the wrong core, we might end up with slow memory as opposed to the fast memory that's nearby. And this is called a non-uniform memory access architecture, NUMA architecture. All right, so it's non-uniform in the sense of performance again. In terms of semantics, you can read from any address you want and it'll work just fine. It's just that sometimes it comes from your local memory, which is higher bandwidth than your neighbor's memory, which is also higher than your remote node's memory. Each one of these is called a node, or this all together is called a node, the memory and the CPU, or and the chip socket. So if you get really unlucky, you run over there, and you access this memory, and then it'll be even slower. I think we should be able to observe that. So there's handy tools. There's many ways we can tell the OS where we want to run. There's a library called libnuma, where you can say, oh, allocate some memory on this node, and run this thread on that CPU only, or on this set of CPUs, or all sorts of stuff. Libnuma, good stuff. But it's a little inconvenient to be editing the source just for that, and we just want to run some experiments. There's a cool little tool called task set. So I'm just going to tell it to run on CPU 0. And then we'll see how long it takes. Okay, that was 2 seconds. We may need to warm it up some. Oh yeah, looks like 0 is kind of far away. All right, and then the way it goes is we have 0 through 8 here. Well, I'm not sure which one is which, right? But 0 through 8, and then 8 through 16, 0 through 7, through 7, yeah, that's how you say it. 8 through 15, 16 through 23, and then 23 through 24 through 31, and then it starts over again with the next hyperthread. So there's 2 hyperthreads, right? So the core number 32 will be back here again, if I remember correctly. So we should be able to check that with an experiment. My hypothesis is that it goes around that way, right? In which case, number 32 should be the same speed. Yes, okay. All right, they're not all the same. AMD likes to number them differently. It goes like all the cores within one socket and then the next hyperthread within the socket. But they don't call it hyperthreads, they're slightly different. Anyway, so let's try this with a different, in fact now let's do a little loop instead. Bash is awesome, learn Bash. Right? Learn how to use this thing because you can save so much time. So here's one thing I like to do. Let's call it core. Core less than, and how many do we have? 64. In fact, because they're hyperthreads, let's not worry about the second set of them. We'll just do like that. So I'll print out the which core, and then we'll run it on that core. Yeah, so Bash is not meant for users, right? It's meant for people like you to look like wizards when you're with the users. All right. So probably the first socket here, there's a slight difference there. I'm not going to make a hypothesis why there's a difference. Probably noise. Oh, there's a hypothesis. Okay, next core. Looks like that was faster, right? In fact, maybe it's sitting on, and then now we're on the next socket again. Ugh. Slow over there. Let's see. Well, we may as well run through all of them and then maybe see if we can form some reasonable hypothesis. Wow, these are really high numbers now. I thought I should make sure no one else is running. I asked them, but sometimes compliance is lacking. Let's see. Oh, it looks good. Okay, so all right, I think at least we can conclude that our file was mapped in see, 7. This should be bad. Oh yeah, the measurement is after. Okay, good. Yeah, so it prints out the core and then the time measurement. So here, core 8 should be different from core 7 because there's 8 cores per socket. So here it goes faster. Oh, and the next one went a little bit faster yet. And then it stayed faster. Any thoughts? Why was the first one a little slower than the rest of them?
We stored some of their pages closer.
It didn't store any pages, but cache lines, yes. Right, so the new socket has its own, the second socket now has its own last level cache. It's a big one. And so some of the contents of our line array perhaps was hanging around in the L3 cache for the benefit of the next core, which is running on the same socket, right? But now the socket, the cache in the socket is populated. Perhaps that's it. In which case, we should see something similar on the next socket. This is a little iffy because I think we kind of polluted the cache already. We ran a whole bunch of things without controlling which socket we were running on, so who knows. But let's take a look. So maybe number 16 is a little slower than the 16. It's a little faster than the other ones. Yeah, so much for that. Anyway, I think it's pretty clear that the memory we're using happens to be on this socket here, right, of core 8 and on. So let's try this, run this on core 8 again. I think it'll go fast this time on core 8. Right. Okay. So we'll stick with that. Oh yeah, I know there's a career fair. If anyone wants to go, needs to go to the career fair, that's fine. I'm recording it. Fingers crossed. We'll also have it published. All right. So we're at 1.1 seconds, and it looks like we're spending about 200 milliseconds in the core, in the kernel, and that's the part where we're mapping things into memory. Can't do much about that other than perhaps shrinking the size of the file, which would probably be a good idea if we could. And then we're spending quite a bit of time in user space. Question is this the fastest we can go? So what are we limited by really here? Sometimes it's very useful to have some kind of rough idea of what is the fastest we could possibly go, so that you don't spend too much time trying to optimize when there's really no point. My wife works in information theory in the ECE department. That's her whole job. It's just writing equations saying how fast things can go. Not programs, but how fast you can communicate over various types of radio links, so that the communications engineers don't spend too much time trying to make a better communication protocol when there's no point. Like, it can go only this much faster, so don't worry about it. And here, same thing. So let's see. We're spending 900 milliseconds, and what is it we're doing really? We're blowing through 100 million of these lines. Let's see how big the lines are. They've grown a little bit, right? We have that reciprocal in there. Can you see it in the back? Yeah. So each point is 2 doubles. A double is 8 bytes. So that's 16, 32, plus another 8, so 40 bytes per line. And it's 100 million lines, so we're blowing through 4 gigabytes of RAM. So, you know, there's probably different limits on what can be done, right? But one limit is how fast can we actually read this stuff from memory, assuming we can compare and whatever as, you know, at arbitrary speed. So we have to at least be able to suck in 4 gigabytes of memory in order to look at it. So in 0.9 seconds, is it reasonable to read through 4 gigabytes of memory? How do we determine that? I think we can just look at the specs. Right? How fast is the memory bus for a chip like this? So let's see. I think this is a Sandy Bridge memory bandwidth. Okay. So Westmere is an older one. Okay, so it looks like in the previous version we could do almost 52 gigabytes per second. That's a big B, so bytes, not bits. Factor of 8. We care about those things. Okay, so, and the other one, 128 gigabytes per second. Okay, so it looks like in terms of the bandwidth, oh, this is inter-processor bandwidth. Let's take one more evidence, let's see. Memory benchmark. What do we have here? Okay, memory reading from this looks like it's probably just from the one DRAM. I don't know. But anyway, even just from one of these chips, because it could be that all of our pages were allocated from the same chip. And so maybe we're limited by that. So let's take a lower bound. But it looks like at the very least, we should be able to do 15 gigabytes per second, not 4. So in terms of just the memory bus, we're good. So we're probably limited by something else. Let's maybe try this with perf. So now we're going to have to use task set, because otherwise things are going to get off a little bit. So let's do it this way. I think that either order would be okay here. You could do perf record on the task set thing, or I think, but we'll try it this way. And probably I need a sudo as well. It's always very hard to type the password when I'm up here. Okay. Okay, that was nice and quick. No error message. All right. Every other time I have to have sudo. All right. Okay, so let's see. What are we spending time on? So this one is a little tricky. In fact, that's I think what I mentioned earlier. That's a comparison. It's an unusual instruction because it's a floating point comparison. That's why I don't recognize it. But we're comparing two registers to each other. That's a really fast one. So probably this is part of our selecting the minimum. Probably that's not it, because a comparison takes a cycle. So even a floating point comparison should be a cycle or a couple. But we are comparing something that came from the stack. So maybe that's a return value, right? And presumably that's from our line list. Now, don't trust this thing. An assignment doesn't necessarily even produce any assembly, right? It all depends. And certainly, this assignment does not produce this. Right. Yeah. So we can't really rely on the C part that much, but it looks to me like we're waiting for this value from line list. That's what's taking time. Yeah.
But you want to start kind of like as far into your stack as possible when you're looking at this. So like if you go back one screen, you'll see.
Well, I'll try. Yeah.
So wouldn't you want to look at like the 19.22 first? Because this is sort of like your stack, and whatever's in line list is probably including whatever's in line store get.
So for whatever reason, this one doesn't actually show self at the moment. I don't get that. Usually there would be the inclusive and the self part. I don't know what happened.
This stuff before main usually. So
was that?
This stuff before main usually? Or this, I'm thinking from start.
Oh, I probably didn't collect the call graph. Yeah, nice. So you're going to run into that exact same problem. Call graph, fourth. So if we don't collect the call graph, we don't know who called. So how are we going to figure out like what's the inclusive cost of main? So in this case, we only got the self cost of main.
So that wasn't showing sort of like a stack, like how things were.
Right.
Okay.
Let me run this thing again, and we'll get probably a slightly different. Okay. So now we have the self as well, but these numbers should be the same. 37, 21, 18, they were probably about the same. Okay, so the question was, shouldn't we start at the sort of the bottom of the stack, because the other costs would be inclusive, but in fact they're not inclusive. That was time spent in main. But here we're getting to this weird concurrency in the CPU deal, right? Because the CPU is actually running 100 instructions at the same time, not running one at a time. It doesn't know which one it's running now because it's running many, right? So you can't account a cost to a single instruction. So we say, well, I said here, we're waiting for the result from this, which one was it? From line list, right? If we go back in here, in fact, I might prefer the other output because this is really messy. We had yeah, actually, I don't really like this inclusive. We'll drop it. And we'll just have to imagine the inclusive cost. All right. So here, I'm saying, oh, this comparison is waiting for the result from line list. But that's ridiculous, because we ran line list before, and it's running sequentially. So how can you be waiting for it? It's already done, right? but that's not really how the CPU works. The CPU, first of all, it predicts that you will be calling it. Well, it doesn't have to predict it. It knows you're going to be calling line list. So it'll call that long before you actually do this. It'll find all those instructions long before we even move all these things into the registers. And then we have these dependencies. Of course, line list, it uses those values that you passed in, so it can't actually run those instructions, but at least now it knows those instructions are coming. Maybe there's one or two it can run right away. Okay, and then it's done with it. Like it goes into it, it issues all those instructions, sticks them in the out of order execution queue, comes right back out because it knows from the ret. It's gonna come back out here, there's no other way. So it comes right back here, and it starts sticking these in the out of order execution window as well. So now you have all these instructions at the same time waiting for each other. This one in particular cannot execute until line list has finished, right? Because it's comparing which one. Let me show you the code just in case it's not obvious. This is the one, right? So we're trying to find the minimum, the line with the smallest distance to the provided point. Okay, so in fact, it is almost like there's messages being sent from inside of line list out to here between pieces of the program that are running at the same time, right? So it's almost like a concurrent program already, even though it looks sequential. All right, so that's why we can't really account for the cost really accurately. I don't know what this is supposed to mean. But I don't know that there's a better number to provide either. I'm sure Intel thought about it. This made sense. It was blocking for a long time on this one. Okay. So, but by reasoning about this a little bit, we can at least figure out that it doesn't take more than one cycle to do the comparison. So the problem is we're waiting for something else. Let's not blame the comparison. Let's go back out. Line list. Okay. It's spending a whole lot of time subtracting two numbers from each other. Well, maybe it makes sense because there's many of these. We're doing 100 million of them. So we should be spending some significant amount of time. But still, these are single cycle operations. How many cycles do we have? Right? We're running for almost a second. So we have 2.2 billion cycles, and we can run multiple operations at the same time. We should be able to run at least 4 billion instructions in this period on a single core. And we're only going through 100 million of these lines. So what are we talking about here? 40 instructions for every line? That seems a little over the top. I mean, these are not that many instructions. So something's holding us up a little bit. All right. Probably it's not the subtraction. But the subtraction is taking these two values that came in as arguments. So maybe passing the arguments in was a kind of a slow thing. Right? And of course, that's going to be slow. We were waiting for this coming from memory. At some point, we were reading this line coming in from memory. Could be that that's what's holding us up. And then we're doing some multiplication. Multiplication is naturally slower than subtraction, so that could be part of the problem. But it could also be some other dependencies. Okay, we probably need to look at something else. Let's try looking at the stat first. In fact, I want to just quickly take a look at this to make sure we're not missing anything. Okay, so here, this is where we're reading from memory. We're just reading in the line. And that seems relatively innocuous. Okay. Some things are going to take time. That's just how it is. All right, let's try this with stat. All right. Okay. So it looks like we're actually doing a whole lot of work. We're getting 2 instructions per cycle. That's not bad. The best we can do, anyone know? On this chip, we have 5 execution units. So the best we can do is execute one instruction on each one of those units, 5. There's some instructions, like some moves, that actually disappear. You don't have to execute them anywhere because they don't have any effect. But basically, if you get to 5, you're doing really well. 2 is great. So doesn't look like at the moment we're blocking on anything. We're just doing too much work. Okay, so that's actually a pretty comfortable situation to be in, because now we can look at the C code and see where are we doing too much work. It's not these weird concurrency effects at the moment. We'll get there probably again. But let's see if we can just get rid of some work. Okay. Can anyone spot anything obvious? Actually, let me oh, sorry. Okay. So this is the part where we're spending time. The rest doesn't matter. So what are we doing that's too much work here?
We keep calling the function line store count every time.
Mm-hmm. Okay, that's a good one. So line store count, that will actually be a function call. You can't get inlined because it's in a different object. So inlining only happens within the same object file, and sometimes you will see that with a .h. Right? If your function is inside the .h, it actually ends up in your own file, in which case you can inline it as well. But so this ends up being an actual call, but then there's just a read, and that'll be in a cache line and an L1 cache. So probably, and the call will run speculative. So basically, yeah, if we are blocking on reading this, if this is like what's holding us up, it will take us extra 4 cycles. But if we're doing other work that's taking more time, those extra 4 cycles would kind of wash away and be part of those 2 instructions per second that per cycle that we're getting in total. Because I know it's a very small part in this case, we're not going to explore it, but it's a good point. Anything else?
We are allocating a new object of line every time.
Yeah, there's 2 things. What did you say? We are allocating?
A new structure object every time. Maybe rewrite the same L.
Is this what we're talking about?
Yeah.
So we're not allocating memory. This is sitting on the stack.
Within the for loop, we are like creating a new object every time. So just if we initialize, like declare it above and just use the same L over and over, rewrite it.
It's actually, so if we read the assembly, you'll find out that there's no work done for the allocation. That part is fine. But there is a problem here. This is a by value return. Right? There's not a pointer to whatever line is in the line store. So potentially we are now, or actually, we are copying those 40 bytes, putting them on the stack. That's the only way to return anything. We're putting those things on the stack, and then we're reading them back out of the stack with a memcopy to put them on, sorry, not out of, this is probably already on the stack, so that's okay, but so we're putting it all on the stack, and then we're reading it out of the stack to pass it in as arguments for the next function. And that's again, these functions here, maybe they could go on the stack, probably because there are these floating point things. Sorry, maybe they could go in registers, probably because of these floating point things they might go on the stack. I'm not sure. Should we look at the assembly, or maybe we skip one step?
Is lines on the heap? On the right?
Lines is an unmapped huge region of, what was it, 40 times, so 4 gigabytes.
So if we just return the pointer to lines, there would we avoid the copying?
Then we'd avoid copying, yeah. So that probably is a pretty good step. But you would want the compiler to do that kind of work for you. Well, maybe, maybe not. Hard to tell. I actually tried that one because I think it has potential. Didn't make any difference at all. And then there's all of this. It's called the line dist, which is manipulating all of these values, reading them from the stack, and then putting them somewhere. So there's a lot of function calls, basically. All right, all these function calls will have a cost. But if they were in the same object file, the compiler would be able to optimize it more. All right, it can inline function calls as it pleases. So why don't we try that? It doesn't make any sense anyway. What is this thing doing? It's reading through the entire line store and finding the closest line. This should be part of the line store object, right? Why is this in here? So we make a, let's see. Oh, what am I saying? Where's the P? There. So min line equals. Right. I was declaring the function here. It doesn't make any sense. Okay. All right. We'll just move that over. I'll leave it there for posterity. Okay, did we have, oh yeah, those are declared here. Okay, good. So that should probably do it. Yeah, I think I've declared it already. I cheated a little bit. Yeah, it's already declared. Otherwise, we'd get a warning. It might still work, but we would get a warning. Okay, so let's try building that. Oh, yeah. Okay, little better. All right, we shaved off 100 milliseconds. Let's take another look with perf. I think we can do better. So at some point, we're going to have to give up on this, right? But it looked pretty promising still. I mean, we had so much memory bandwidth. We have so many instructions. So many instructions, like multiply our 800 milliseconds by the 2.2 gigahertz by the 2 instructions per cycle. Like, there's a lot of instructions per line here. We should be able to go a little faster still in a single thread. So let's see. What happened? Oh yeah. So we're not spending any time in main anymore, right? Because I moved the whole thing into line store. So that's good. Line store get is entirely gone, right? That used to be a big thing. If we look a little closer, maybe we'll see. Let's see. So is it like this? Okay. Where's our line store get? Sometimes I guess if you do it with a call graph, it'll say, oh, this part got inlined. Right? It doesn't indicate it here, but doesn't matter. So basically oh, here it is, actually. Nice. So it says line store get. This part came from line store get, right? And it's actually doing whatever line store get was doing, it's doing that inside of this closest function now. So we didn't have to do that function call. That's really nice. So what are we spending most of our time on here? Which one is this? Let me back out. Closest, okay. Okay, so this is still a big one, right? Comparison. of the previous min with the current distance. And then was there anything else that was big? Maybe we don't have to worry about those right now. Yeah, seems like that comparison is the biggest. Okay, so what's going on in that comparison? This is called a line dist, and line dist happens to be part of another object. Okay, fine, let's move that into. Sometimes you have to make sort of a judgment call here, right? It's not good to pull in all the functions from every C file that you know of into the same object. But this is an extremely tight loop that we're doing. That's basically the whole program. So it's probably worth a little bit of change here. So there's two things we can do here. We can either move this line dist into the .h, in the geom.h. This is a geometric function, so it should be in the geom object. That makes sense. If you put in the .h, you might get multiple definitions of this. You'd have to put some if-defs around it to make it okay. Like if you're including that in multiple files, compiler would get upset, or linker would get upset. Just to keep it simple, I'm going to cheat a little bit. I'll just put it here. So now the compiler knows, because remember, when the compiler is compiling something in C, it takes us one C file, produces one object file, the binary is done. Right? That's all that it does with the instructions. And then there's linking. It just resolves some addresses. Like there might be a jump, and it figures out what should be the right address to jump to. There might be a move from some global or whatever. It'll know where that global is by the time it's linking. But it's not rewriting any instructions. So for optimization purposes, it's over after you've dealt with one C file. Okay, so now we are allowing the compiler to optimize this stuff, basically to inline line dist into here as well. See if that makes any difference.
So why wasn't it inlining before?
Right, so line dist was part of this geom.c. I apologize for the small font. So geom.c makes a geom.o, and that will have all the instructions for line dist. And then linestore.c makes a linestore.o, which would have all the instructions for closest, which calls line dist. But it doesn't know what line dist is yet. It just calls it, so that's just a symbol. It says, okay, jump to this address. And that address gets resolved when you're linking the programs together, the object files together. But it doesn't know what's in there at all.
The linker won't inline.
Linker cannot inline.
Yeah.
The only thing a linker does is replace relocation entries with actual addresses. That's it. If you're curious about this sort of thing and you haven't seen it before, there's some good 361 lectures on this. I recorded some. I can post them on Piazza if I haven't posted them anywhere else. Just to see like how you go from a C program to an executable, that sort of thing. Also take the compiler class. That's a different story, but it's a cool class. Okay. Right. So now the compiler can choose whether it wants to inline this. It won't always do that, but hopefully it'll see that this is a big loop. Let's see. Okay. So I needed to include this math.h. This actually works without it. It's not entirely obvious why it would work on a float. Well, anyway, we'll live without it for now. Okay. So we knocked another 300 milliseconds off of there. Let's take another look. So you might think, oh, what's another few hundred milliseconds, right? But we were at 1 point, depending on how you count, maybe we were at 2 seconds, maybe we were at 1.5, 1.2 when we started, right? And now we're at 0.5, so that's actually well, maybe we should count this. But it's a doubling in speed, which means now we're using 10,000 machines instead of 20,000 machines, which is a nice savings. You know, save the world kind of savings. Okay. Yeah, we were going to run perf. Right, so it looks like it did inline all of that code. So now we're just sitting in line store closest doing this loop. And then there's all this other stuff, but you see it has a K in it. And that means this is kernel work. So most of it is just mapping pages. And it's actually mapping and unmapping pages. Right. So all of this happens when we do the mmap. Because I told it to do it eagerly. Well, map populate. Right? I said just map everything in at once. It'll be a little faster than getting a page fault every time you access a new page. But what about all the unmapping? I didn't tell it to unmap anything. Why would it be unmapping pages? Garbage collection? There's no garbage collector. C doesn't have garbage collectors.
What about destruction?
Sorry?
Destroying objects going out of scope.
Yeah, it's not not objects necessarily, it's the executable going out of scope. So when the program exits, we've mapped in all these pages. What does it mean to map in a page? Well, it's sitting in a page table. But that's fine, we can just free the page table, who cares, right? What the contents are, just mem set that to 0, be done with it, right? But there's also some accounting, because the OS needs to keep track of who's actually using this part of memory. Right? This page got mapped into that process, so it's gonna have to at least decrement a reference counter, maybe decide if it should evict this page, probably not, but stick it somewhere else. So there's some work to be done, and there's quite a bit, it's 4 gigabytes worth. So it's 1 million pages that we're doing this for. It's a fair bit. Okay, but we can't do much about this stuff. The best thing we could do is probably to try to make our that cache file smaller. Maybe that could be helpful, but let's not worry about it for now. So the rest of our time is spent in here. Okay, we're still on that comparison. What else do we have? Look at this. This is beautiful. See how little code it is? Right, it's almost just a screen worth. So the compiler did a good job, I think. So what are we doing? We're reading the stuff from memory. We're doing a couple of multiplications, which we can't avoid, and we're doing a comparison. At this point, I'm probably going to give up. There's a couple things we can do to go even faster. Well, there's one thing I know we can do to go faster on a single core, but that's going to have to wait a few weeks. We could try to resort to SIMD instructions. That's single instruction, multiple data, or you may have heard of vectorized instructions or vectorized code. Basically, you can say, oh, do these 4 at the same time. So let's load these 4 values, let's divide them all by 100, and then store them over there. Right? So we can do, sometimes we can do 4 at a time, 8 at a time, depending on the size of the registers. And not the registers. Well, on the specific processor family, and then the size of the values that you're moving around, if it's floats or doubles. So we could probably try that, but that's a whole nother topic. Let's just drop that for now. So at this point, I think single-threaded performance, I don't know how to go any faster. But maybe we could try multi-threaded, right? So it looked like, actually, let's see if we can do another stat. Yeah. Okay, so it looks like when you have this sort of thing, it's usually because there's a lot of waiting, or in our cases at least, it's because we're waiting on dependencies. Right? It's not that this front end couldn't figure out which instruction to run next. It's that the whole speculation window is full. The backend isn't asking for anything. The backend is waiting for some dependency on a load or whatever. It's not asking for any more instructions. And we got nothing to do in the front end. That's stalled. So probably this is because the CPU here is just waiting to get some stuff from memory, and there's some latency for these things to take effect. But we're still not hitting the bandwidth limit of the socket. Right? We should be able to go 15 gigabytes per second, and this is taking half a second. So we probably can go faster. It's just that this core is just maxed out. So let's try using another core, or some more cores. I think we'll do this with OpenMP first. So there's two main ways of doing multi-threading, and the one that you've seen in the past is probably pthreads, like task-oriented multi-threading. That's awesome, because that is reality. Right? You start running something on a CPU, and it runs there until it's done, unless it gets switched out. That's really that's the only way that the CPU provides multi-threading. But there's another little tool called OpenMP that's provided by GCC, not by Clang. For some reason, they haven't done that yet. But so this is called data parallel programming, where you kind of tell the program that, okay, this part of the program can run in parallel. So in this case, we'll say this loop can run in parallel. And then the compiler figures out the rest. So what it's going to do in this case, and I'm going to use OpenMP only because it's very convenient in this case, for starters. So we say pragma omp for parallel 4. And that's that. You know, you've done pthreads programming. It's a pain in the ass compared to this. On the other hand, this is really ugly. Right? It's not even part of the language. It's some weird macro thing going on outside. It's going to be really hard to reason about properly. But whatever, we're doing a simple experiment, so in this case, let's do it. So what is this doing? OpenMP decides on the fly how many cores are available, and it'll start that many tasks. And in this case, because I didn't specify any more parameters, and there's a ton of parameters here, you can specify all sorts of weird stuff for the parallelization. But I didn't say anything else, so it's going to, in this case, we have 64 hyperthreads. It will start 64 threads. It will split the loop. You'll probably read this once, because it's not, I think this one's not volatile, so we'll probably read it once. And we'll just run each chunk, excuse me, each chunk of this 100 million, split it into 64 pieces. Each of them runs a little piece of their own. And then we're good. Okay, let's just see what happens first. Okay, just to have a comparison, let me run the time thing. There. Right, so we're at 500. Okay, so in order to support OpenMP, you have to specify this flag, which I did in advance. And let me get rid of that ugly warning as well. It didn't go faster because I included that. I hope it didn't go faster because it included. It probably went faster because I included that. There's a decent chance that because I didn't at first specify what type it was, the compiler did something generic to provide the parameter to this fabs. I didn't say what type it was, and so maybe it stuck the value on the stack in some standard way, and then I don't know. Oh, that doesn't make any sense. Well, usually when you provide more constraints, the compiler sometimes can do some more optimizations, and probably that's what happened here, and we won't explore that hypothesis any further. Okay, so it went a little faster. But anyway, it's already pretty fast. Oh wait. I already built a new one. That's why. Okay, sorry. I forgot that I rebuilt it. Let's try it out. Oh. Yeah, I did. Thank you. I should hit the pragma. I was just looking for an ugly hash. That was the wrong one. There. Okay, of course. Well, that's better. Okay, yeah. So forget my my thing about the .h there. In principle, I think sometimes it's possible that you might have some optimization there. It didn't happen this time. Okay, so it went a little faster with this OpenMP, but it didn't go a whole lot faster. In fact, it's kind of surprising it went faster at all. Can anyone spot my error? It's right here. I told it to only run on core 8. That's not all that useful for a parallel program. So I don't know why it went faster. Let's give it another core. That didn't really help. Okay. Let's just not be so picky. Okay, so what's going on here? I was looking at the user, because that's the one I usually look at. Right? This is how fast it went before. And then it went a little bit faster, and then not, and then slower, and then really, really crazy slower. But it didn't take 21 seconds, right? That was not 21 seconds.
It counts each thread separately or each core separately?
Yeah.
Is that its own time?
So the user time is how much CPU time are we spending in userland. And so now we're using 64 threads, I think. Probably 64, maybe 32. And we're spending a lot of time on each one of those. The time that really matters, I think, is the real. Right? How long did we spend until it was finished? And so that went from 700 milliseconds to 700 milliseconds. Not great. But look at this. Somewhere in between, it's actually going faster. So here we're just using 3 cores. That's faster than when we're using 64 hardware threads. Yeah?
It has to do with the comparison for the minimum. It's like they're waiting to do the comparison.
For the minimum, yeah. So I think let's just look for one more thing before I forget. There's something else that's really interesting here. Can you see what the problem is? If you stop looking at the time.
The value incorrect.
Yeah. It's not returning the same distance. I provide the same point, but it's returning different distances suddenly. Right? What's that? That's a race condition, yeah. So we wrote this program for OpenMP, and we figure OpenMP is magic, so it should be fine. Unfortunately, it's not. So all OpenMP did was start 64 threads and then run all these in parallel. And so they're all comparing against their own version of MinDist, or some old copy of MinDist. And then they're seeing, okay, mine's better, and it's overwriting, and then maybe it gets overwritten by something else, just in a random order. So we don't actually have a good grasp on which one is the min.
If you made MinDist volatile, would that change?
Doesn't fix it, unfortunately. What we need is a critical section. We need to have a lock around MinDist in order to to do that. Okay, before we get there, I wanted to do, we have 4 more minutes, so we're in good shape. I wanted to do a couple more of these experiments. In particular, I want to add all the cores on this socket. See how fast that goes. Okay, so 0.4, let's see. I want to see what is the fastest we can go. Maybe. Okay, looks like we're not going to go any faster at the moment. 0.4. But now, unfortunately, it's producing incorrect values. In fact, this is pretty good, but they're, no. All right. We're on the same socket. You're going to get a little bit better consistency because there's shorter latencies to the memory. It's less likely that they would overwrite each other's stale values. But yeah, you can't trust it. So we have to acquire a lock around here. OpenMP provides a very nice way to do that. This just means whatever is after this line, within this block, within the for loop that it's in, this is going to use a single lock. So all of these threads use the same lock. They acquire the lock, then they execute the rest of it. So now we will get the correct value. And you know, we could compare it against the single-threaded version we had before to know what the correct value should be. Yeah, that's fine. The other error comes from a different old stale target. All right. Any guesses? What's going to happen before I run it? Slower, yeah. Okay, let's see.
It was slower before, even, there's the race condition on min-dist, but then it's not like they're actually waiting to like write to min-dist. So is that really why it was slower before?
Excellent question. Why did it go slower? If we didn't have a critical section, why would it go slower when you add more threads? Right? Yeah, so the problem is whenever you write to a cache line, you have to acquire exclusive rights to the cache line. So basically you have to tell everyone else, this is mine now. And they have to at least tell you, okay, yes. So every write goes a little slower if someone else has it. If it was already in your core, it's really fast. If it's on your socket, it's pretty fast. If it was on a remote socket, you may have to wait for a while. But that's okay. There's this thing called store buffers, which we'll talk about later. But unfortunately, as you add more cores, they're all fighting over this. In the end, you exhaust your store buffers, and you can't make any progress until you get that cache line. And that's when you start seeing some waits. In this case, it's much worse, because now we actually explicitly have to get the lock acquired. Atomic instructions are really slow, but now we get correct values at least. Let's try this with no limit on the number of threads too. Right, so with an atomic instruction, the deal is the instruction does not, everything serializes. So you have all these instructions that you were hoping to run in parallel, but now comes an atomic instruction saying, compare and exchange this value with this value. Nothing that is after in a series of instructions can execute anymore. The CPU will just stop until we've finished executing our atomic instruction. All of your cores, in this case 64 of them, do the same thing. They stop and they wait for everyone else in this case. There's a long line of 64, all right? They're all just waiting for the previous one to release the cache line. And so now you have 64 threads that are basically just waiting for each other and not able to execute anything in parallel. So we lose both the parallelism of the having many cores, and we lose the parallelism inside the core because we use this atomic instruction. And you see it's still not finished. So we can do much better, and I will, yeah.
Is it okay to make a suggestion?
Sure.
I have a question in response to this. Would you be able to do like have each thread have its own minimum, and at the end compare all those minimums?
Exactly. That would be a great solution. It's complicated in OpenMP. So I think next time we'll write the same thing in pthreads, just a little more lines, but it'll be easier to reason about, and we can do something proper. There's some, I think we'll talk more about OpenMP a different week. There's tricks you can pull with it too, but it's all outside of the language, outside of C. It's this separate OpenMP thing, which is a little unfortunate. It's useful, but not, depending. But yeah, still not finished. I don't know when it's going to finish, so let's just go home. Have a good one.
Is there like a data structure that we can write to from like a bunch of different threads that isn't gonna like lack, and then we can put all of the distances in there and then like punch them all afterwards?
We'll do it next week. Sorry, the next lecture. Yeah.